Hello, in this video I'm going to show how to solve for the force between a infinite line charge and a semicircle, just centered at that line charge and wraps around like so, drawn this picture. We're told that the line charge has charge density or charge per unit length lambda L. The semicircle has charge per unit length lambda C. Okay, so and the circle has radius R. Okay, so to solve this, like many other problems involving finding forces or fields due to charge distributions, I'm going to, let's pick a color, green. I'm going to divide the charge distributions into segments. So I'm going to divide the line charge into little segments of length dx, and the circle charge into little segments d theta, where that angle there is theta. So d theta is the change in angle, rotates up a little bit. So that little segment is of length. The length of that segment is r d theta. Okay, so I want to find the force between these two segments. So I'm going to draw a line between the two of them. And the force, assuming they're both positive, which we will for now, if one of them is negative, it'll just point in the opposite direction. The force between these two line segments points off in that direction. I'm going to call this dF because it's the force due to just a little, due to the differential line segments. We'll integrate it to get the full force. Okay, so that's the situation. We have a little the dF is the force between this segment and this segment at angle theta, d theta dx. And we can refer to this distance here as x. Why don't I draw, to be clear, why don't I draw a coordinate system? I'm going to call x the direction along the line. I'm going to call z up, and y over there. So my final force between these two, by symmetry, the force has to be in the z direction because the x and y parts cancel. The x parts will cancel because a segment over here will cancel with the segment over there. The y parts will cancel because the segment over here will cancel with the segment over there. So we can say Fy equals Fx equals 0. The question is, what is Fz? Okay, let's get started with this. To find Fz, I first need to find the two little charges, this little differential charge and this little differential charge there. So I'm going to write those out as dq1, that'll be this little differential charge here, is equal to the length times charge density, so lambda L times dx. dq2 is equal to lambda C times r d theta, because the length of this little chunk is r d theta, so the charge of this little segment here is lambda C r d theta. Okay, so now what I would like to do is I would find the force between these two. So the force, well, I'm going to call it dF because it's the force between the little differential segments, is dq1 dq2 over 4 pi epsilon naught r squared. R hat, we'll put a vector on that, where r is this distance here, the distance between this segment and this segment. Note that r is not the same thing as capital R, which is the radius. Okay, so this here is the force, the differential force of those two little segments. It's a vector. It points off in some bizarre direction because, well, it's just direction directly away from this little chunk here. I'll point off that direction somewhere. We only want the component in the z direction because well, the other ones will cancel. So first one I'm going to note is I'm going to see, well, this force is pointed off It is really bizarre angle. Not only is it not it's not straight up like it would be if you were pushing on the top of the circle, but also points over to the side. So to find the component of that that points in the z direction, I'll first find the component of it that points in the radial direction. You can imagine, say, an analogous thing if you were pushing right on like this end charge, the charge at the end of the circle there, some fraction of it would be that force would be the radial, some fraction would be x. We, of course, don't care about the x. We only care about the radial part. So we'll find the radial part, and then I'll find how much of that radial part points specifically into the z direction. Okay, so to find the radial part, I'm going to say that r hat r over r hat. That means r hat is going to be the r hat, remember, is the points directly away. So it's the part that points directly away there. R hat sub r is the component of that that points directly away from the center of the circle, the radial component of r hat. I'm not going to draw that in there, but it's the radial component of r hat. So the radial part of this unit vector over the unit vector itself, so the fraction that points in the radial direction, is r over r, where capital R is this, r is that. This is by similar triangles. You can draw those similar triangles out. I'm going to draw them over here. So here is r, r. The radial part points out there. It's a continuation of the big R. This is a continuation like this. This is r hat. This is r hat sub r. So you can see those are similar triangles. You can use trig to work out this relationship down here. Okay, so that's the radial component. And I should note there's little r's in both of these. We can figure out what little r is. Little r by, if this is x here, we can use trig to find that. Little r is the square root of r squared plus x squared. So, but this is only the radial part. We don't care just about the radial part. We care about the part that's in the z direction, because some of the radial part points off in the y direction, which we don't care about. So we're going to find the components in the z direction. Well, that's just sine theta, the part that points straight up. Remember, if theta is 0, it all points in the y direction. Sine of 0 is 0. If we look at if theta goes to 90 degrees or pi over 2, then it's pushing at the top of the circle, and then all the radial part is pointing in the z direction. So basically, to get r hat that's in the z direction, we are going to need to put in a sine theta. So sine theta r or r. Okay. So putting this all together, we can say df. Let me zoom up so like handwriting is a little better. df is equal to q1, q2. I'm just going to write those as q1, q2 for now. We'll substitute them in later. Over 4 pi epsilon naught r. Oh, and we want the z component of df. So 4 pi epsilon naught r squared plus x squared. So that gives us r squared. So that's this r squared here. And then the r hat that points in the z direction is sine theta r over r. But r is square root of r hat plus x hat x. Okay, so now we're going to combine that whole thing, this whole thing together. I'm going to substitute in my two dq's. Sorry about that. So I'm going to substitute in the two dq's, and I'm going to get d f in the z direction is equal to lambda 1, lambda L, lambda L and C, I guess what I call them, L and C, and R squared, because we have one R from here, and then when we stick in this down here, we're going to get an R from there, so R squared over times sine theta over 4 pi epsilon naught r squared plus x squared to the 3 halves, because you can combine the to the 2 halves plus 1 half is 3 halves, and then d x d theta. Okay, we want the full force. So force in the z direction, we're going to integrate both sides. So we're going to get the full force is the integral. I'll put in my limits in just a minute, so I'm leaving some room for them, of lambda L lambda C r squared sine theta d. I'm going to switch the order, d theta dx. You can always switch the order of integration. 4 pi epsilon naught r squared plus squared 3 halves. Theta is going to go from 0 to pi, and x is going to go from minus infinity to infinity. Why is that? Well, you remember the problem itself up here. Theta goes around here. It goes from 0 to a pi. It's half a circle. We're doing it in radians. Things always work out better in radians. X is an infinite line, so it goes from minus infinity to infinity. Okay, so that's that whole thing there. So now we've got it down. That's the force in the z direction written as an integral. So now physics is done. We're down to just doing math. This is the whole integral. Now we just need to do an integral, or well, do 2 integrals technically. As it turns out, sine theta is the only part that depends on theta, and you can pull that out. So we can actually separate these 2 integrals, fz minus infinity to infinity. Actually, let's pull out constants to make this even simpler. So lambda L lambda C r squared over 4 pi epsilon naught. And then I'm going to write one of the integrals. So integral from minus infinity to infinity of 1 over r squared plus x squared to 3 halves dx. And then I'm going to write the other integral, 0 to pi sine theta d theta. Why was I able to separate these? Well, because the bottom here depends only on x, and the top here depends only on theta. So it turns out that this particular formula can be multiplicatively separated like this. That's not always true of double integrals. But when it is, it makes them much easier to do. So now these are actually fairly straightforward integrals. Well, okay, not that straightforward. Sine, you can probably remember the integral. Integral of sine is minus cosine. The integral of this thing, that one's a little more hard. I would just look it up. Happens to be, well, I'm just going to write it out here. Z is equal to lambda L lambda C r squared over 4 pi epsilon naught. And then I'm going to write this as a square bracket. And if you do that integral, you look it up, the answer turns out to be x over r squared square root of r squared plus x squared, evaluated at minus infinity and infinity. The other integral of sine is minus cosine. Even I know that integral. Cosine of theta that gets evaluated at 0 and pi. Okay, let's stick these in. F z is equal to, this is getting boring writing this thing over and over again, but whatever. R squared over 4 pi epsilon naught. And then this is going to be, okay, if we stick in infinity, we get infinity over x squared square root of r squared plus infinity squared. But you'll notice that that x, when it goes to infinity, this r is irrelevant because it's r plus infinity, so that this infinity dominates the square root. It then becomes the square root of a squared infinity, which goes back to being just infinity, and then it cancels the infinity on top. So it turns out those two cancel. Don't believe me, you can use L'Hopital's rule. Similar thing will happen with the minus infinity. We get minus a minus infinity over r squared square root of plus, and this is also infinity squared. And once again, the same thing happens. The infinity dominates the square root and then cancels with itself on the top. So we get that there. And this cosine of 0 is, or cosine of pi is -1. So minus a -1. Minus, and then a -1 again, because cosine of 0 is 1. So you have minus, and then this -1. So this is 2. This integral is 2. Both of these integrals happen to be 2. How you like that? So this is 2. This is 2. That all cancels out and give, well, sorry. This one is 2 over r, capital R squared. So that capital R squared, let's do this in red, cancels this. And we end up with force is equal to lambda L, lambda C. The two 2's cancel the 4, and I get pi epsilon naught. And that, ladies and gentlemen, is the z component of the force, which is all of the force because the x and y components are 0, and that is our answer. Interestingly, it doesn't depend on r, but we should check the units. So if you recall, let's do this in a different color. If you recall that force is equal to Q1 Q2 over 4 pi epsilon naught r squared. So this is just Coulomb's law. You'll notice that I don't remember what the units of epsilon naught are, but in order to get force, I need to multiply by charge per length and charge per length. You know, Q is charge, length squared. Lambdas are charge per length in and of themselves. So charge per length and charge per length over epsilon naught. So these two things have this thing here and this thing here have the same units, the units of force. So yeah, the units work out. So units work out. Turns out not to depend on r. It just depends on the two charge densities. Okay. Good luck with the rest of the homework.